Good morning, all. Am I audible? Is it fine? Is there anyone in the comment section? I mean, sorry, in live. Do let me know in the comment section. Please respond. Am I audible? Okay. Kanaka, Savita, Pratika. Okay, done. Good morning, guys. So, today we are going to enter into the most important part. Of course, it's very beautiful too. Three-phase circuits. Why this part is very important and it's beautiful is our entire world, this universe is just we are transporting the power with the help of three-phase transmission lines only. You can see wherever you are in travel, whether it may be a bus or cycle, you during during walking also, everywhere you can see the transportation. Our carrier, simply called three-phase transmission lines. So with the help of poles, we are continuously expanding the power system in order to carry the power from one place to another place. Even we are trying to transmit this power to the remote areas also. So that's the beauty of our three-phase system, and our entire world is as of now adapted with this wire, the three-phase system where we are in which we are trying to carry the power. People also doing the research to transmit the power with the help of wireless transmission, like that is in progress. But as of now, our beautiful system is simply adapted to the three-phase circuits only. And there are some advantages why we are going up with the three-phase circuits, what is the major reason, and why can't we go with the two-phase, why can't we go with the single phase alone. Basically, in electrical network theorems, you might have observed so far we have been dealt with the only single phase circuits. We haven't traveled along with the three phase circuits. Sir, already we are analyzing all the circuits with the help of single phase or single phase, and we will be able to transmit the power in single phase successfully. Single phase circuits means simply you can transmit the power to the load with the help of a single wire. That single wire will be carrying the power from the source to the load, and you can connect variety of loads with this. I am simply demonstrating with the help of one or two loads, and successfully we can do like this. We can connect any number of loads that you want in parallel connection, etc. It will be keep on continuing. So these type of connection, single phase connection, where you are having, can you tell me, do we have single phase circuits in this universe? Though we are studying about single phase, I'm just asking you, do we have single phase circuits? Yes, of course, sir, we are having. But where we are having? Next question. In our home, small applications. In our home, we are having single phase AC circuits only, sir. Yes, of course, that is true. You are correct. Anything else apart from that? Actually, what happened is in earlier days, after finding this power, three-phase power, we are unable to transform the more number of power from there is more amount of power from one place to another place. So people started thinking about it. For an example, initially there were only one fan or one TV in each and every home. Nowadays, what happens? Everything switch out to electric circuits. including our vehicles also is going to be transmitted to electric. Electric in the sense what will happen? The power consumption or power demanded by the people is continuously tremendously increasing. In order to overcome this issue, we were started adapting to the three-phase system. People started increasing the number of phases through which we are trying to carry the power. Sir, from single phase, immediately the next one is two phase. Yes or no? Yes. So first they have started analyzing the two phase circuits. Is it possible to carry the power with the help of two phase lines? If you observe in single phase line, what we need to do, whenever we are trying to push the current, it is in forward path. This is traveling like this. But we know in order to carry the current, we always need a closed path. If we need closed path in the sense, if you are keeping one wire to transmit the power, you must keep one more power to receive the current. So here your current will be transmitted. This is called forward path, and here your current is returned to the same position where it is terminated, where it is originated. So the conclusion is in order to carry the current, first thing is closed loop is required, and starting point and ending point must be the same in case of closed path. Now people started analyzing the two-phase circuit. In two-phase circuits, when we are trying to push the current through the two phases, we are injecting two current I1 and I2. So basically what they understand here is when the moment we are trying to transmit the current through the two phases to the load, what happened here is the phase angle difference arises. Suppose if the phase A, let me call phase 1. If phase 1 is carrying the current of 10 at an angle of 0 degree, then immediately phase 2 is started carrying the current at 10 at an angle of minus 90 degree. First, they figure out that the current carried by the two-phase system is producing the phase angle difference of 90 degree. Why I am putting 90? Because in two-phase system, if phase A current is entering first, that is phase 1 current is entering first, after 90 degree, phase 2 current started appearing into the system. So there is a 90-degree phase delay between them. After that, once they started reach the load, we must provide the return path for this two-phase system. Actually, in the load, if you observe, what will happen is two currents are getting summed up. Let us call it as I1 plus I2. So what is the net value? When we are adding these two currents, suppose you can take this at same 10 ampere as the example. You know 10 at the angle of 0 can be written in rectangular form as 10. 10 at an angle of minus 90 can be written as minus J10 in rectangular form. So the net current will become 10 into 1 minus J. In order to carry this current, we need a return path. So we are also providing one return path to the system. So this is what they found in two-phase. Immediately they have started analyzing the three-phase system also. They have taken three-phase. Three-phase means once again they have started analyzing with the help of three wires now. So in three wires they have started injecting the current. Let us say I1. Second phase is carrying the current of I2. Third phase is carrying the current of I3. After analyzing this, what they found is here these currents are started producing the phase angle like this. Phase A current is producing the phase angle is 0, I at an angle of 0. You can take the same example. Let us take 10, 10 at an angle of 0. And then, 1 minute guys. Phase 2 is started carrying the current of 10 at an angle of minus 120 degree. Phase 3 is started carrying the current of 10 at an angle of plus 120 degree. They have understand this. Next, what happened is, okay sir, we have produced these things. So they immediately started, okay, these three phases are carrying the current of I1, I2, I3. Now we should connect them with a load. Let us connect it. So when they are connecting it with the load, after that, we need to discuss about the return path. Let's see what happened here. When the moment they have summed of all this current, let us take current I1 and then current I2, then current I3. There was a surprising things was waiting for them. What happened is when they have started adding all this current through the load, let us take the current through the load is the algebraic sum of current I1 plus current I2 plus current I3. What happened is when the moment we are trying to add all this current, it came like this: 10 at an angle of 0 plus 10 at an angle of minus 120. Guys, for your understanding, I have taken the magnitude is 10. You can take any value magnitude, okay, that is I. 10 at an angle of 120, 10 at an angle of plus 120. This resultant value will be heals to 0. They were really very excited and surprised. Oh my god, what happened here? So when we are doing in two-phase system, we have done the same thing. This is the resultant load current, but the resultant load current became 10 into 1 minus j. This is resultant load current. But if you observe the same thing in three-phase system, resultant load current became 0. You can simply inject it with the ground. That's all. Conclusion what it is here, there will be no point of keeping one more return path because there is no return current. Return current will be 0. So in three-phase system, they have identified that when the moment they are injecting the current in different angles, how you will draw the waveform for this? Suppose I am injecting the phase A current at 0 degree. Just understand like this. Okay, you know it will be 0 instant, it will be 180 instant, it will be 360. Suppose if you people are injecting the current at 0 degree, first current, its maximum magnitude is 10 into something root to 10 by root to something. Next, see this is 180. So 120 may be here. This is 90 degree. We know sinusoidal will reach its peak value at 90. Again, it will reach its negative peak at 270. Now I am planning to inject the second current in three phase. Second current will be starting after 120 degree. So first current is entering at 0 degree. Second current will be starting from here. 120 plus 180 will become 300 somewhere here. So it will be reaching its maximum value. Then it is going back. So this is 300. This point is 300. So they have started traveling like this. This is the second current. Now, so this is 120 degree point. So first one is phase 1 current. Second one is phase 2 current. Again, they have started injecting the third current. Third current is what? It will be appearing. See, this can be written in two ways. Either it will be 10 at an angle of plus 120, or you can also write it as 10 at an angle of minus 240. Both points are same only. Minus 240 in the sense, from phase A, 240 degree it is lagging. Second phase is lagging 120 degree from first phase. Third phase is lagging 240 degree from the first phase. 240 means where it is. Between 180 and 270, 240 is lying. Yes or no? So, third phase current is started appearing from here. So, this is what they found later on. Okay, sir, fine. So, after that, what they have figured out is they figure out one more thing. What the things, what are the things that they have figured out it here? The thing is, if you add these three phase current at any instant, this phase 1, phase 2, phase 3, addition of these three currents will be always heals to 0 only. So return path is not required. Just with the help of these three current, just with the help of these three phase lines, we can carry this total current. Return path is not required. Additional current. So have you figured out here? See there, here just with the help of three phase system, three phase means with the help of three wire, we are carrying more current. Here one 10 ampere, here one 10 ampere, here one more 10 ampere. If you observe in two phase also we are having three wire. Two wires are for forward path, one wire for return path. But here we are carrying only two current because only two transmission lines are carrying the current in forward path. So here we are overcoming one advantage. If you go up with the two-phase system, definitely three wire is required. But out of three wire, only two wire will be carrying the power in forward path, and another one wire will be act as a return path for this forward path current, total current. But the advantage of three-phase system is without providing the return path, same with the help of same three wires, we can carry additional current. So the power transmitted, the amount of power that will be transmitted from the sending end to receiving end with the help of three-phase line over two-phase line is more. That is the first advantage. And the second thing is, usually what we are doing, our entire modernized world is interlinked with mechanical power. Mechanical power means in our home, we are using refrigerator. In our modern entire, almost every one of us started using a refrigerator, air cooler, induction motor, mixie, grinder. Majority of our electrical component that we are carrying in our home appliances, not only in home, in modern residential, commercial, everywhere, industries, are started converting. Basically 90% of this energy will be converted into mechanical form once again. Mechanical form means it's a kind of rotational energy, yes or no? Basically, in all type of mechanical systems that we are carrying in our home, we are having fan. Rotating fan will be there. It may be a cooler, or it may be a mixer, or it may be a grinder, whatever it is. So majority of our mechanical components are carrying some kind of rotational system, that is mechanical system. So in that mechanical system, what will happen is the current that you are injecting will be what he is doing. See, let us go ahead with the next one. When I am trying to transform this power, okay, sir, successfully we are transmitting the power from sending end to receiving end with the help of two phase and three phases. Then at the receiving end, what will happen is we are carrying a mechanical system. In that mechanical system, we are having a rotational part that is called a rotor. So this rotor basically not having any interlinking with the stator. Between stator and the rotor, we will have a air gap. So in that air gap, basically what will happen is the amount of electrical energy that we are injecting through the stator first will be converted into magnetic energy. Then that magnetic energy will be converted into mechanical energy. This mechanical energy will help the rotor to rotate properly. Now we should check. People started thinking about it. We are having, what they have done is first they have injected two-phase system, then they have injected three-phase wire system. In two-phase system, two currents are entering, phase 1 current, phase 2 current. So phase 1 current, suppose if it is having some normal current, general current I at an angle of 0, then definitely phase 2 will be having I at an angle of minus 90 degree. Only these two currents are being injected into the stator in case of two-phase system. They are producing pulsational torque. There will be no unit torque. Pulsational torque means what? Pulsational torque means machine will not rotate properly. There will be a jerk. You can observe the vibration inside the machine. Of course, we can call it as major noise. It may lead to damage the system as soon as possible because its lifetime will always will be reduced drastically, and more noise will be keep on coming if you put this system inside the home everywhere. That sound, if you switch on the fan, immediately a very huge amount of noise started coming out of it. So that is the one more drawback. But they have started doing the same thing. They have started doing the same thing with the three-phase system. Three-phase system will be producing 120-degree phase angle. This is the smooth waveform. First current will enter at 0 degree, second current will enter at 120 degree. After one more 120, third current will appear. So this beautiful system, he started making a smooth rotation without any pulsation. That is one more beautiful advantage why we people are started traveling along with the three-phase system. You understand the future, no? This type of questions you can expect it in 1 mark. Why we are not giving priority for two-phase circuits? Why we are directly going up with the three-phase circuits? So these are all the advantages why people are not giving importance for two-phase system. Okay, fine, sir. Now you might have understand the reason why we are carrying three-phase system. Let us go ahead with our three-phase system now. So in order to increase the power transmission ability, basically what will happen? Let me model our power system. So if you take our power system, we will be basically carrying one alternator, that is a single phase equivalent circuit. It is called a single line diagram. You might have heard about this in power system. It is called single line diagram. Just I am representing a basic circuit of a power system. Then we will start analyzing it. So here we are trying to carry it with the help of a transmission line, equivalent circuit of the transmission line. Then it will be connected with the various types of load. Basically, load means we will be treating induction motor. I told now there are so many loads, but majority of our system is carrying induction motor only. Anyway, you can also keep some other loads that you want. So here we are going to carry alternator, our superstar. This is our transmission line. These people are, this is called bus feeders. Bus. We can call them as bus. So this is the basic single line diagram. Here usually what we are doing is we are trying to transmit the three-phase power. Yes, sir. We are trying to transmit the three-phase power. This is single line diagram, but basically what will happen? We will be carrying three transmission lines. Okay, sir. So if you observe most of the cases from this is called a transmission line. So let me break it. These lines are called a transmission line. The lines which are connected with the lines which are connected with the alternator and the big transmission lines, right, which are connected with the big bus bars, they are simply called a transmission line. The line which are connected with the loads, the lines which are connected with the loads are called distributed lines. So there are two lines. Transmission line basically carrying the power from the alternator for a very long distance. Then that transmitted power will be distributed to the loads, various loads. That is called a distribution line. That's all. Distribution line. This name will appear only at the end of loads everywhere, because they are simply distributing the power that was carried by the transmission line for the long distance. Now what will happen, sir? If you observe, basically we are using three-phase alternator here. This three-phase alternator will be generating the power through three phases. And there the current will be like this. Phase A current, suppose let us take I at an angle of 0. Phase B current will be I at an angle of minus 120 degree. Phase C current will be I at an angle of minus 240 degree or plus 120 degree. Both are same only, don't forget. Okay, sir. So if you observe these three phase current from the alternator, they are carrying same amount of current. Magnitude of the current will be same. First conclusion. And the second conclusion is, if you observe the frequency offered by these three phases, that will also be remain same. So there are two conclusions. One is the three phase power that we are transmitting from the sending end will be having two things same, common values in all the three phases. One is current, another one is frequency. Current and frequency, current and frequency. Similarly, voltage also will be same only. Magnitude of the voltage is V at an angle of 0 degree here. Here it will be V at an angle of minus 120. Here it will be V at an angle of plus 120 or minus 240. But sometimes these phase angles will be different for the current. It depends on the nature of the load at the receiving end. That will be later. I am just discussing the common points. So here the conclusion is, then what what is the difference between three phases? The only difference is phase angles. If phase A will be entering at 0 degree, if phase A current will be entering at 0 degree, then the next current will be entering after 120 degree. That is called 120 degree lagging. I am drawing it in x and y axis. Don't think I am doing something that you guys not knowing. This is x and y axis only. In the x and y axis I am projecting. First current I am fixing at y axis. Then second current will be fixed at a 120 degree lagging. You know, I told you lagging means negative. Whenever you are keeping something in something at a negative angle, it should be in clockwise direction. Positive angle means counterclockwise direction. So from phase A, the first current will be fixed at 120, second current will be fixed at 240 somewhere here. So the total phase angle from here to here it will be 120 only. From phase A to here it will be 240. See, now if you observe the third current, let us see, let me show you. Let me call it as phase A current, phase B current, phase C current. Phase B, if I am calling phase A, its magnitude is high at an angle of 0 degree. Phase B is placed with the same current, but it is placed at an angle of minus 120 degree lagging. Similarly, phase C, if you observe, from phase A it is having 240 degree. Yes or no? Lagging. In the alternative way, if you observe in counterclockwise direction, it is 120 degree leading. Both are same point. Yes or no? So I can write either it is 240 degree lagging from phase A, or I can also say it is 240 degree leading from, it is 120 degree leading from phase A. Both are correct. See, if you observe in the counterclockwise direction, our perception is plus 120. In the clockwise direction, our perception is minus 240 degree. That is how we are projecting these values with the help of phasor diagram. Just it is a representation. Okay, sir, that we understood. Next, is there any classification in the three-phase system? So let me come to the conclusion. So in the sending end, there will be no issues. They are flowing properly, and I told you magnitude of the current, voltage, and frequency all are common at all points. The only difference is phase angle. So this phase angle sometimes it will be different. So now it is fixed. From the sending end, we are very happy. We are having 0 degree, minus 120, minus 240 or plus 120. So whenever we are trying to add these three current, resultant value will become 0. So people understood that return path is not required at the sending end. But slowly, when they have started distributing this power to the loads, what happened is, due to the different characteristics of the loads, we are connecting variety of loads. We are not only connecting induction motor, we are also connecting variety of loads. Okay, sir, when we are trying to connect different loads, what happened? The loads that we are connecting with the system is started affecting the natural behavior of the system. Sir, what they have done? The story is started here. What happened is, we have started feeding the beautiful current with the help of three transmission lines. Yes, sir. So all these three transmission lines are feeding the power to the load. Yes, sir. But this load, what it started doing is, it started producing some kind of unbalanced current. Unbalanced means what they did, sir. Unbalanced means they have changed the property of the source usually carrying the current like this: I at an angle of 0, I at an angle of minus 120, I at an angle of minus 240. They have introduced some changes in the space angles. Because of this space angle changes, this net current will be 0 only at this particular angle. It should be at minus 120, minus 240 or plus 120, both will give you same value. Only at this balanced phase degree, your net value will become 0. If there will be any changes in this phase angle, suppose if this suddenly this minus 240 will be raised to minus 270, or it is reduced to some 200 like this, what will happen? The resultant addition of this three phase current will not become equal to 0, sir. It will be having certain value. This problem started arises at the end of the loads. So what can we do now? We have to do something. What we have to do? Very simple. Sir, in the distribution side, three lines are not sufficient. We need one more line. That line is called return path. Why, sir? Why? Because so now this is called a distribution line. From the transmission line till the end of the transmission line, I was trying to carry the power with the help of only three-phase line. But now in the distribution line, due to the variety characteristics of the different loads, I have started observing that the balanced current will become unbalanced now. This unbalanced current, what happened? Unbalanced means the resultant addition of the three-phase current will not be equal to 0 in the distribution side. So in order to carry the resultant current from this addition of three-phase, we need one more path, that is called distribution line. Now you can observe near to your home. Definitely you can observe, suppose it doesn't matter whether you are in village or you are in city, hometown. Anywhere, if you observe the system, at some places you will have your transmission line will be having three lines. If you observe the lines which are near to the load, homes or industries somewhere, Those lines are having four lines. Why? This is called a distribution line. In this distribution line, there may be a chances of getting unbalanced current. That unbalanced current will be carried by one more written path. That's why we are carrying these four lines. And observe this carefully. These four lines will be tied in a pole. They will be tied at a pole for each and every 50 meter. We will be keeping nowadays. Nowadays we are keeping 50 meter only between the poles. So in each and every poles, if you observe, we are carrying one insulator will be there. That insulator will be carrying this transmission line, sorry, distribution line. But I said I put only for three transmission line. I said there will be one more line, that is called return path. For this return path, if you observe, it will be simply tightened at the pole. There may not be any insulator for this, because it is simply called a return path. This return path may or may not be carrying. It depends on the behavior or characteristics of the load. So at sometimes there may be a current, and sometimes there may not be a current. Okay, it's simply carrying neutral line or ether line. Most of the cases it will be zero only, because your load, if whenever you are trying to switch on, suppose if your entire village is switch on all type of load, in that cases you can observe this return path current. Anyway, the conclusion is this fourth line is simply carrying the, what I can say, unbalanced current. Okay, so that's why we are carrying one more line in our distribution side. Okay sir, we understood all the basics. Now from the transmission line, from the sending end till the receiving end, is there any variety categories in the three phase? How we are basically carrying these three phase lines, sir? How they are connected together? Now see there. Suppose if I am having a three phase line, I am having a three phase line like this. How we are connecting this three phase line together? So they people started using two ways. Let me show you. We should join this three phase line, right? They are going to start, what I can say, they are going to carry the power together only. But how they are going to be interconnected each other? What type of connection we are going to provide for them? Three phases should be connected together. So they have started thinking like this. Then first we found one method. So one person is connected the line like this. Yes. So one person is found like this. Just they have started playing the game. Okay, just we need to connect all the lines together, right? So they made a common point. In that common point, all the lines are interconnected. This is one way someone found. Another line, one more person, what he did is he created one delta triangular. Then he just joined all the edges of the triangular with this. So they found these two circuits. Later they named it. This is called. See, it seems like a star connection simply. So they simply name it as star, star three phase star connection. And this is also they have accepted, and they simply name it as mesh. See, it is closed loop, right? So this circuit is called mesh circuit, or we can also call it as delta. So it is also named as delta mesh. Mesh means it's a loop. It's a loop or not? See there, if you observe, it's a loop only. It is a loop. So delta connection, it's also called mesh connection. It is a closed loop circuit. Star connection is also called open connection. Delta connection is called a closed connection. If you observe, see, star is open only. Do you have any closed path here? No. Everything is open. Phase is open. But in delta, phases are connected together, closed each other. Then they have giving one more name. They have started giving the name for this. If we are measuring the current between these two lines, there are three phases, right? Phase A, phase B, phase C current. If you are measuring the current between the two phases, they kept one more name, that is simply called line current. If you are focusing only per phase, then they have started calling it as phase current. But see, remember one more thing. Always while doing the measurement, we need two terminals. Yes or no? If you are connecting the ammeter will be having two terminal. One terminal will be connected with the one end, and another terminal will be connected with the another end. You cannot connect simply one terminal with this something and you cannot find out the reading. So in order to take the reading, we always require two terminal. Suppose if that two terminals, if you are connecting the ammeter between two phases, then the measured current is called a line current. But in the star connection, when I am trying to measure the phase current, see only phase current, only one phase current, single phase current. The single phase is having only one terminal, but in order to measure this phase current, I need one more terminal. So in star, people also found one more line that is called neutral line. This neutral line will be called earth line. It will be simply connected to the ground. Now I can measure the current between one phase and the ground. Ground will be carrying 0 ampere. You don't want to be bothered about it. Now if I will measure the current between this phase and this earth line, that current will be called phase current. You can repeat the same thing for other phases also. So whenever we are trying to whenever we are trying to do the measurement between the two lines, that is called line current. Same thing you can also keep for the voltage, line voltage. If you are trying to do the same thing for per phase, then that is called per phase voltage and per phase current. Now raise the next question. Sir, okay, I understood. You are saying that we are having two type of connection. One is called star connection and another one is called delta connection. We understand everything. And in a star connection, we are having two type of measurement. One is between the lines, we can do the measurement between the lines. Another one is between the line and earth point. So if I will do the measurement between the line, then that current is called line current, and if you are doing the voltage, then that is called line voltage. If I am doing the same measurement for a single phase, then that is called per phase current, and voltage will be called it as per phase voltage. Similarly, you can do the same thing for delta also. If we are measuring the current between these, see, if you observe, this is basically it is having three line. Suppose if I am measuring the current here line to line, then that is called a line current. Voltage will be line voltage. Similarly, where is per phase? See, this is one. There is I am taking only one phase. This phase is having two terminal. If you observe, the phase and the line both are same only in case of delta. So here what will happen is if I will find the potential difference between these two terminal, that voltage is called what? Per phase voltage, and the current through this per phase line is called per phase current. Now what is the difference between this line and the phases, sir? In case of star connection, sir, I am skipping the derivation just to focus on it. In case of star connection, basically we are adapted with the three-phase system. Now I am talking about three-phase system. So if we are in a single phase, suppose if we are in single phase, then we will have only single phase voltage and a single phase current. But while calculating apparent power, I requested you to take conjugate. Don't forget. This is for single phase system. Only one phase. One phase will carry only one phase voltage, one phase current. When we are adapting it with the three-phase system, this is for single phase. When we are going up with the three-phase system, it will be three times of, see, there are three phases. This is phase number 1. We can call it as phase number 2, phase number 3. All the three phases will be carrying per phase voltage, per phase current. So totally we are having three times of per phase voltage into per phase current, and don't forget to take conjugate. Fine, sir. This is good. It's absolutely fine. And this is called three-phase system. Same thing you can put. This three-phase power formula is common for both star and delta. Either you can consider star or delta. This formula will be remain same. Okay, sir. This is three-phase per phase power. Suppose if I am trying to write this power in terms of line voltage and line current, what will happen? Let us see. When we are discussing about the star connection, in case of star connection, if you observe, see there, let me take, this is the line. Suppose if I am injecting any current here, line current, let us take I am injecting a current of I1 through the line. That current will be coming like this. See there, after reaching this node, it is entering into phase. If you observe, the line and phase both are connected in series. Yes or no? Simply understand. Don't think too much. Then I can say line current and phase current both are same in case of star connection. So if two currents are same, then we can call it a series connection. That's why it is also called series winding. I told there are more names. This is star connection. We are also calling it as open windings because windings are open. It's not like delta. Delta having mesh, but star is not having a mesh. It is also called a series winding. But if you observe the voltage, see voltage we are measuring. If when we are trying to measure the line voltage and the phase voltage will be different. Line voltage will be giving root 3 times of per phase voltage. See, for this we need a phasor addition. I have done in our course. You can observe this. Okay, I don't want to waste my time here. So line voltage will be having root 3 times of per phase voltage. Okay, sir. Fine. Now, if I will substitute these two values, so from this what I can say, in place of phase current, you can substitute line current, but in place of line voltage, if you want to write this, see, if you want to replace phase voltage in terms of line, then you have to do like this, line voltage divided by root 3. See what I'm going to do is I'm taking the same power, but think like this. I'm having only line parameter. Then how do I write? You can write like this: 3 times of phase voltage can be replaced by line voltage divided by root 3. Both are same only. Just now I have been proved it. Phase current and the line current both are same in case of three-phase circuit. Three-phase star connection, not in all. Okay, sir. Now, how will you reduce this? This 3 can be written as root 3 into root 3. If you observe, 1 root 3 will be cancelled with the denominator. So, this can be further written as root 3 times of BL IL conjugate. So, in order to calculate the three-phase apparent power, either you can go up with a per phase parameter or you can go up with a line parameter. If you are going up with a line parameter, then root 3, factor root 3 should come. If you are going up with the per phase parameter, then you have to multiply it by 3. Chalo. Let us repeat the same thing for our delta connection. In case of delta, see, if I will inject any current here, see, this current will come here. After reaching this junction, if you observe, there are two paths. Current will be divided. So I can't say that phase current and line current both are same. So here, this relation will be coming like this. Line current will be equal to root 3 times of phase current. It will be derived from the phasor diagram. I am not drawing this. It will be waste of time. Okay, just to do remember. But if you observe the voltage, see there, when I am trying to measure the potential difference between these two terminal and these two terminal, both are same or not? In between this terminal and this terminal, we don't have anything. Similarly, between these two terminal, we don't have anything. So I can say these 2 points are same point only, and these 2 points are same points only. Then what will be the conclusion now? From this I can say line voltage and phase voltage both are same in case of delta connection. So when I am trying to measure the power, once again, single phase power, three phase power, same formula will be derived. For three phase, in terms of phase voltages, it will be 3 times of per phase voltage into per phase current. But we must take conjugate, don't forget. And if you are trying to write the same power in terms of line parameter, then phase voltage and line voltage both are same, but phase current, if you want to write the phase current from here, how will you write? This can be written like this: phase current can be replaced by line current upon square root of root 3. If I will replace it by line current upon square root of root 3, we must take conjugate, don't forget. Then as usual, this 3 will be replaced by root 3 into root 3. 1 root 3 will be cancelled. Once again, you will be coming up with the same root 3 times of VL into IL conjugate. So what we have understand from here? Sir, it doesn't matter whether you are traveling along with a star connection or delta connection. In both star and a delta connection, the power transferred value will be same only. There will be no difference in case of power transmission. After identifying these two networks, they figure out this one, and they also found the voltage difference between these two things. Yes, sir. That is the one more important thing that you must keep it in your mind. So here, though we found that the line current and phase current both are having same magnitude, there will be a difference between the phase angle difference. If you observe, they both are not in phase. There will be a phase angle difference between line current and a phase current. Similarly, if you go with the delta, in delta, magnitude of the line voltage and the phase voltage may be same, but they won't be in phase. In phase mean they will not be in phase. There will be a small phase angle degree between line voltage and the phase voltage, that is called 30-degree phase voltage. The phase angle difference between the line current and the phase current is 30-degree. Here also the phase angle difference between the line voltage and the phase voltage will be 30-degree. Now I am giving a small task to you all. Immediately raise the next question. Sir, whether it is lagging or leading. Similarly here, whether it is lagging or leading. That is your task. Spend your time. I already told you to go through all these points because this is very important point. You can expect direct one more question. That's why I am highlighting this point here. Okay, spend some time. Just go through what is the exact phase angle difference between line current and phase current in star connection, line voltage and phase voltage in delta connection. If you know the answer, kindly drop it in the comment section. Okay, fine, sir. Now you might have understand the difference between star connection and delta connection completely. And it is very important to know the conversion, because at some places there will be a need of conversion between star and delta. Let us see. Suppose I'm having a star network. I know many of you know this, so just to have some time, patient. Slowly we will be starting the lecture. It is my responsibility to recapture everything. Three phase is very bit important, a little bit. If you are undoubtedly started solving the problems in three phase, it will be help you to crack the questions in automatically machines, power system, power electronics. Okay, because they all are adapted to the three phase circuits now. Fine, sir. See, let me call it as A, terminal B, terminal C, and I am calling it as neutral terminal. I am naming it as N. This is star connection. Suppose people are asking you, can you convert it into equivalent delta? Proofs are there, but I am writing the relation directly. I don't want to prove it here. Same terminal. I'm not changing the terminals names. Okay, same terminal, but they have restructured it. ABC. They have taken the same terminal. They have restructured like this. Delta. So if you are restructuring it like this, then if you observe now the impedance, now I am trying to measure the impedance between A and B. Here it is B to C or C to B. Here it is C to A or A to C. Anything is correct only. It doesn't matter which terminal you are taking first. Okay, sir. Now, how do I transmit this? Suppose I want ZAB. So we are transmitting the impedance from star to delta. How will you calculate this? If you observe, ZAB is connected between terminal A and terminal B. Look into the star connection. In terminal A, we are having the impedance ZA. In terminal B, we are having the impedance ZB. Just to multiply them. And in the denominator, keep the total impedance. Overall impedance offered by the star connection ZA plus ZB plus ZC. Similarly, you can repeat this for ZBC. When we are traveling along with the BC, what will happen? The available impedance in the star is ZB and ZC upon the overall value will become ZA plus ZB plus ZC as usual. Repeat the same thing for the third impedance. ZAB, ZBC, ZCA. You have to write, very simple. Suppose if I am having a delta connection. Sir, I am having a delta. I would like to transform it into equivalent star. How will I do that? They are also having same terminals. Let me teach you. I am having as usual impedance terminal A, terminal B, terminal C, and the impedance we call it as ZAB, and here I am calling it as ZBC. Here it is going to be ZCA. Now its equivalent star. A same B same C. What we are trying to do? We are converting into star connection like this. That will be a necessity. Okay. Let's see. Let me write it here. How will you write this? In star connection, suppose if you want to know the impedance of the first phase ZA, here I am placing it as ZB and ZC. How will you write ZA here? Yeah, எல்லாரும் face இவ்வளோ serious வச்சிட்டு பார்த்துட்டு இருக்கீங்க. Keep some smile in your face. I told now, you know the reason also. இது வரைக்கும் நீங்க அதை பண்ணிருந்தீங்கன்னா practically நீங்க experience பண்ணிருக்கலாம். Our brain is the complete activity of the brain is என்ன சொல்றது நீங்க மூஞ்சிலே பார்த்துடலாம் நம்ம ஃபேஸ் ஹாப்பியா இருந்தா brain is happy because both are interconnected each other. Just keep some smile in your face, nothing is wrong. Okay, fine. ZA எப்படி எழுதுவீங்க? ZA can be, if you observe, ZA means a terminal A. So just to check, in the terminal A there are two impedance connected, ZAB and ZCA. If you observe, we are having two impedance, so this can be written as, can we write like this? So let me write this one is, 1 minute guys. Yes, so let me write. So when we are writing this relation, how will you write? So we are having two terminal here, ZCA and ZAB. So just I think there is some small mistake that I did here is, 1 minute, I think I have confused the derivation. It is A, it should be, 1 minute, I'm proving it. Am I doing any mistake here? Yes, I'm confusing myself. For a 6 month gap, it automatically still, though I'm, yes. Sorry guys, my derivation went wrong. Kindly forgive me. Let me do it again. When we are going from delta to star, that's why I'm getting wrong relation. Okay, fine. See, suppose if delta is having A, B, C and it is having three impedance. Let me call it as ZAB, ZBC, ZCA. And I need ZA, ZB, ZC. So I'm calling it as terminal A, terminal B, terminal C. Now here what will happen is, I do remember actually what, while going from delta to star, always in the numerator, if you take in star C, here we are going to consider the point A. If you observe the same point in delta, whatever the branches that are connected in that common point, it should be in product. It should be in product. Denominator, we can add all the values, ZAB plus ZBC plus ZCA. Similarly, if you are observing the second point, that is ZB, how will you write this? ZB means second point. If you observe the same point in delta, there will be two common branches, ZAB, ZBC, which are connected with the second, point B. So this can be written as the product of ZAB into ZBC upon the overall value, ZAB plus ZBC plus ZCA. Similarly, if you observe the third point, ZC, what is the third point? Here we are having two branches, ZBC and ZCA. So it can be written as ZBC into ZCA upon ZAB plus ZBC plus ZCA. So this is delta to star transformation. Okay, kindly forgive me. I had a little confusion in the derivation. It's not because of the lagging unconsciousness. Fine. Now when we go from star to delta, in star as usual we are having impedance A, impedance B, impedance C. But in delta we are having between the phases ZAB, ZBC, ZCA. So here I am calling it as ZAB. This one I am calling it as ZBC, this one I am calling it as ZCA or ZAC, whatever. Under terminals are, again I am naming it as ABC. When we are going from this way, if you want to write the value of ZAB, what you have to do is, see, ZAB means we are talking about A and B, two branches. So here, if you observe, in A we are having the impedance is called ZA plus. In B we are having the impedance is called ZB plus. We have to keep its product ZA into ZB. Now if you observe, only one branch is left now. A and B we are considering, C is missing. That branch impedance will be lies at the last. Similarly, if you take the cross product, it will become ZA into ZC plus ZB into ZC plus ZA into ZB upon ZC. Okay, it's very simple. Do remember, at last I will tell you one trick here. Similarly, if you write the expression for ZBC, how will you write? ZBC means it will be the addition of ZB will come first, ZC will come next, ZB and ZC will be multiplied here in the denominator. The missing impedance is ZA. If we do the cross product once again, you will come up with the ZA into ZB plus ZA into ZC plus ZB into ZC upon the value will become ZA. Now similarly, if you write the expression for ZCA, it will become ZC plus ZA plus the product ZA into ZC upon ZB. If you do the cross product once again, it will become ZB into ZC plus ZA into ZB plus ZA into ZC, ZA into ZC upon ZB. Observe the common points now. See, if you observe the total numerator, product of A into B, product of B into C, product of C into A. See there, product of A into B, product of B into C, product of C into A. Product of again A into B and then B into C, C into A. So what we have observed, the common point is numerator of these three are same. When we are transforming the impedance, when we are trying to calculate the impedance of the delta from star, its numerator will become common. If you observe the delta to star, denominator will be common. In that case, denominator will be common. Yes or no? That is the observation. So here what you can do, if you found the numerator for only one person, you can keep the same value for all other person. In the denominator, what you must do, suppose if you are calculating impedance for A and B, denominator should be C. For B and C, denominator should be A. For C and A, denominator should be B. Like that, it will be very easy to while doing the calculation. Now, one more conclusion. So there are two type of load. One is called balanced load and another one is called unbalanced load. In case of unbalanced load, in case of if the load is unbalanced, then the impedance ZA may not be equal to ZB. Let me write somewhere here. In case of if the load is unbalanced, then what is the meaning of unbalancing, sir? Unbalancing in the sense impedance of phase A, impedance of phase B, impedance of phase C are not equal to each other. Balanced load in the sense if the load is balanced, then impedance of phase A, impedance of phase B, impedance of phase C all are equal. Okay, sir. With the help of this, what can we do? If the load is unbalanced, then only you have to derive these expressions and you have to substitute all the values to calculate the value of A, B, B, C, C, A or ZA, ZB, ZC. If the load is balanced, strictly I can say, see, if the load is balanced, then we can keep a common name for all the impedance Z. Let's see what will happen. When the load is balanced, then see that in place of ZCA, I can put Z here also, you can put here Z, denominator Z. Then what will happen? Numerator Z power 2, denominator 3Z. So it will become Z by 3 only. 1 Z will be cancelling. Same here also you will come up with Z by 3. Here also you will come up with Z by 3. Repeat the same thing for delta also. See when this one in this case, in case of delta network, when all the impedance are same, Z square, Z square, Z square, denominator only 1 Z. So 3 times of Z square upon Z, it is cancelled. So here I am getting 3 times of Z. Here also you will be getting 3 times of Z. And here also you will be getting same 3 times of Z. What you have understand here, when we are going from delta to star, when we are going from delta to star, if the load is balanced, while going from delta to star, if the load is balanced, then impedance of the star will be equal to impedance of the delta divided by 3. That is the relation between star and delta. And you can reverse from here. Similarly, I can say when we are going from star to delta, if you are going from star to delta, then we can say impedance of the delta will become 3 times of impedance of the star. Same from here. If you pass the 3 here, you will get the relation that I have proved just now. See there, this one. I am getting 3 is that only. So do remember this. It is only applicable when the load is strictly balanced. Otherwise, you can't use this formula. But don't forget, it is very important. Okay. Kanaga Savita. Line voltage leads 30 voltage. Line voltage leads 30-degree phase voltage. Line current lags 30-degree phase. Good, good. So you are talking about that delta star phase voltage, phase voltage, line voltage, phase current, line current difference, right? Very good. Star delta formula Matthew sir. Yes, I did now. Small confusion happened. Forgive me. Just skip this portion. Take this now. Similarly, I have been talked about apparent power and everything we have done. Let me talk about, apparent power can be written in two ways. One is in terms of voltage and current that I have written already. Now, how do I write it in terms of power? Same, there will be no difference, plus or minus jq. But what is the formula to calculate the real power? If you are calculating it in terms of per phase voltage and per phase current, 3 times of per phase voltage into per phase current into cosine of phase angle difference between the current. Same formula. This is 3 phase power. Same 3 phase power. If you want to write this parameter in terms of line, how will you write it? It will become root 3 times of line voltage, line current into cosine of phase angle. Similarly, if you write the apparent power, reactive power, it will be 3 times of per phase voltage into per phase current into sine phi. If you are writing the same 3 phase power in terms of line, it will be root 3 times of line voltage into line current into sine of phi. Okay, it is very important. Okay, this is one more thing that you guys have to remember in your mind. Okay, sir. Now, I have also requested every one of you to go through the power measurement. I am just giving introduction with the help of wattmeter. It is name itself, it is called wattmeter. So it is helping us to measure the three phase power. Of course, we can also measure single phase power. Here broadly we are focusing on three phase, but it doesn't matter. It can't measure single phase. It is measuring single phase power also. So while calculating the three phase power, it will also indirectly helping us to estimate the value of reactive power. How will I do that, sir? From this wattmeter measurements, if you observe the phase currents and voltages, there will be a final value, right? We must calculate the power factor. You will be requested to calculate the value of power factor. This is the first value in three phase. How do I calculate the power factor from the measurement of wattmeter? Let me derive one by one slowly, then you will be understanding fully. So phi is equal to directly, first we are calculating tan inverse of two things. In the numerator, if you observe, we will be keeping root 3 times of reading of the wattmeter 1 minus reading of the wattmeter 2 in the numerator. In the denominator, it will be simply reading of the wattmeter 1 plus reading of the wattmeter 2. This is the common point that we are comparing. So here, if you observe this numerator, this is the formula to calculate the reactive power. So what you have to do is, you have to take the reading of wattmeter 1, subtract it with the reading of wattmeter 2, multiplied by root 3 in order to obtain the reactive power. So to know the real power, just add the reading of wattmeter 1 plus reading of the wattmeter 2. Okay, you might know the reason for this. Kindly go through our measurement lecture. I have broadly classified everything. I have derived step by step why it is with the help of phasor diagram. So here I don't have that much time to do all those things. Just recollect it by yourself. Just to go through the lecture of measurements that I taught. So this is the phi. Once you calculate the value of phi, from this you can estimate the value of power factor cos phi. There is some twist. Sometimes they will be giving you the value of power factor. you will be requested to calculate the value of W1 and W2, or that is reading of the wattmeters, or you may requested to calculate the value of reactive power, or you may requested to calculate the value of reactive power. You have to do everything here. Okay, these things are a little bit important. Just keep your eye on it. Remaining things anyway we will be covering in measurements, how it is coming, and what is the basic voltage formula behind of this, that voltage current into cosine of 5 plus theta, 5 plus 30, 5 minus 30. We will be dealing with all those things now, so that things will be dealing in measurements. But it is very important to remember these basics. Without knowing this you can't do. Okay sir, one more thing. This formula you can use as usual only for source. I told na, whenever you are trying to put the total voltage, total current, that will be dealing with the source only. You cannot use this formula cos pi et al for individual loads. So when you people are dealing with the individual load, individual impedance, what will I do, sir? Very important. Yes. So if we are calculating the per phase impedance in case of star connection, let us go ahead. If I am going up with the star connection, how will I do? Per phase impedance means it will be per phase voltage divided by per phase current. According to Ohm's law, Z equal to V by I. If you want to write this parameter in terms of line, how will you write that? In star connection, you know line voltage equal to root 3 times of phase voltage, or per phase voltage can be written as line voltage divided by root 3 upon phase current, and the line current both are same. So what you have to do is line voltage divided by line current into 1 by root 3. So don't forget this. So here itself I can write similarly. So per phase impedance of the star connection will be written like this: line voltage divided by line current into a factor of 1 by root 3. That is the actual relation in terms of line parameter when you are trying to estimate the per phase impedance. You so you have to understand this. That is very important. So when they are trying to do this same thing, like okay sir, from this if I am trying to observe the power, how will you calculate the power? If you want to know the total power consumed by the per phase apparent power, you know the formula is either you can use per phase voltage, that is V phase square, upon what will you do, that is per phase impedance divided by Z phase. Yes, sir. V phase square. Suppose if you want to write it in terms of line, then also you can write. There will be no issues, right? So either you can put this is per phase I am writing. So when I am multiplying it by, if I want to know the total power, system is balanced, sir. All the phases are having same power. Then you have to multiply it by 3. So it will become 3 times of per phase square divided by Z phase. You can also use phase current. It doesn't matter. Okay, this is the generalized formula. Here, suppose if we are writing a line parameter, observe, it is very important. When we are substituting the phase voltage, then this is the formula. Okay, sir, still I am in star connection only. Just observe the total impedance. So that will be 3 times of per phase, total apparent power, 3 times of per phase apparent power. So here what will happen is, so when I am trying to write 3 times of per phase voltage, you know per phase voltage can be replaced by line voltage divided by root 3 whole power 2 divided by, I can substitute per phase impedance now. If you elaborate it, what will you obtain? So it will be 3 times of VL square upon root 3 whole square also will become 3 divided by Z per phase. So 3 will be cancelling out here. Yes, sir. So in terms of line parameter, you can observe it will be simply VL square upon Z phase only. This is the total apparent power. From this, I can derive that the per phase impedance equal to VL square divided by apparent power. So you know in three-phase circuits, basically we will be talking about per unit impedance calculation. In per unit, people will use to say like this. In per unit, there is one impedance is called base impedance. Base impedance will be derived from actual line voltage and apparent power. See this, this is actual line voltage and actual apparent power. So this base impedance only we are calling it as base impedance in three-phase circuit. Per phase base impedance. So the formula in case of star connection for per phase base impedance is line voltage square divided by apparent power. Sir, why are you specifically defining it for star? In delta, what will happen? Let us start and derive all those things step by step. So let me do the same thing for delta. Let's see what will happen when we are talking about delta. As usual, delta per phase only I am deriving. So what will you do? Per phase voltage divided by per phase current. You will be doing with the same one. But you know, in delta, line voltage and phase voltage both are equal divided by, but phase current will be equal to line current upon square root of 3. So you will be coming up with the factor of root 3 times of line voltage divided by line current. First conclusion. See there. Here if you observe, the factor is 1 by root 3. But now if you observe here, the factor is root 3 because here the difference is phase current will be line current divided by root 3. But there is voltage, right? That is the first conclusion I am deriving. Second, we will be talking about the, okay, so this is conclusion number 1. So I can say what? Delta, in case of delta, per phase impedance can be written as root 3 times of line voltage divided by line current. Don't forget, this formula is very important. The derivations are very important. Don't memorize anything. Understand? Okay. Next, suppose when we are trying to calculate the total power in case of delta. So this can be as usual 3 times of per phase power. How will you write? 3 times of what? How will you do? Per phase voltage square divided by Z base. First we have to calculate the power consumed by per phase. Then you can multiply it by 3 in order to obtain the total power consumed by the loads in 3 phase. How will you write it further? It can be written as 3 times of, sir, we know in case of delta, line voltage, phase voltage both are same. So in place of phase, directly I can replace it by line. So line voltage square divided by Z phase only. This is for total apparent power in case of delta connection. Observe the difference between these two. It will be 3 times of VL square upon Z phase. For delta I am doing. Don't forget. See, in case of star, the impedance is what? If you observe, the apparent power became what? Simply VL square. Total apparent power will become simply VL square by per phase impedance. Without undoubtedly I am deriving it. Don't forget these things. Here if you do 3 times of VL square, 3 times of the factor 3 is appearing or not? That is the difference. From here, if you calculate the value of per phase impedance, it will become 3 times of VL square divided by apparent power. So, this calculation is only for delta, whereas this is for star. I have derived it clearly. So if you observe in three-phase system, base impedance, when we are calculating in per unit calculation, when you are trying to calculate the base impedance of three-phase system, in case of delta connection, you will be requested to keep 3 times of VL square divided by apparent power. This is called base, line base voltage. Basically, they will give you line voltage only, base voltage. And this is base apparent power. With the help of these two, you can calculate the base impedance. But here factor 3 should come. But in case of star connection, that 3 should not come. See here I am having 1, not 3. Okay, so it is very important to remember these two relations, otherwise you will be in trouble. So because why this factor 3 is keep on coming, sir? We only derived that. 1 minute, let me prove it. What I told you, we only derived that the impedance of the delta will become 3 times of the star impedance. So it is just proportional. This factor is reflecting everywhere. The impedance of the delta will become 3 times of impedance of the star. See, let me prove here also. The impedance of the delta, it will be equal to 3 times of VL square by S is nothing but impedance of the star or not. See there. VL square by S is nothing but impedance of the star. Perfect impedance of the star. That's why this factor 3 is keep on coming everywhere. But without remembering this basic, people are thinking unknowingly they are keeping that we don't know how these three came, sir. These basics are there somewhere in network analysis or somewhere. So it is very important to remember these fundamental basics while solving the problems in case of three-phase circuits. Otherwise, you will be in trouble. Okay, these things you should apply when you are dealing with the individual impedances. When you're talking about a specific resistor or a specific inductive reactance or a specific capacitive reactance. Okay, just do remember all those things and recapture one more time. Okay, try to solve some problems from your side also if it is possible. Remaining things we will see in the next class. Okay, I have covered all the basics almost. I don't think that I left something. Whatever the things that are required for three phase, that I have covered. Okay, in network analysis, if something is left over, that will be covered. We will be dealing with those part in where, in case of electrical machines and power system. Basically, when we are going up with the star and delta connection, you all know there is some different types of current will be introduced in the three-phase system. They are simply called harmonic analysis. Effect of three-phase harmonics, effect of fifth or third order harmonic, fifth order harmonic, and how they are influencing in star connection and delta connection. Those impact need to be analyzed in electrical machines and power system, not here. Almost I have covered those things already, and again I will be covering in machines and power systems in the upcoming lecture. So with this, let's wind up the today class. Remaining things we will say.